Hi, welcome to this follow-up video of the RGB shift PWM lighting. In this video, I will cover up few points and ideas that I think I might have missed in the previous video. If you don't have any clue of what I am talking about, please click on the link here to see that video. First, let me explain about my barebone Arduino build. This is a simple perf board which has a ZIF socket mounted in it. Ideally, it should be a 28-pin ZIF socket, but I was in a hurry and the shopkeeper did not have what I required. So I had to buy this one instead and just use the top 28 pins. I also have a screw terminal here in which I have connected the crystal and the picofarad capacitors. I have used these instead of soldering them directly because if I wanted to experiment someday with the 8 MHz crystal, then I should be easily able to swap it. Why use screw terminals, you may ask? I could have easily used female headers. Well, I tried that, but it wasn't making contact properly because of the thin legs of these picofarad capacitors. So I swapped them with these, and now I'm sure that they are always connected. I also added a big heatsink to this voltage regulator because I don't know in which future code how much amps the circuit is going to draw. So a big heatsink is always a good idea. Apart from that, there is a switch to toggle the power to the Atmega chip. There is a DC jack through which I can deliver 12 volt to the circuit. It's a simple build, but it has been really helpful for me to build all the circuits. In my previous video, I showed you the schematics of Elko Jacobs, but I split into two modules. One is the controller board which will have the Atmega 328 chip, and the second will have 3 shift registers which will connect to the RGB LEDs. I split them into two for easy troubleshooting and mass production. Well, not mass production exactly, but just 5 boards. Anyway, here is the controller board which has the Atmega 328 chip and the rotary switch. Because I will be using a DC socket like this one and a switch, in the schematics I replaced it with a terminal socket over here and here. Also, after the code is processed, I need to send them to the shift registers. For that, I have used some more screw terminals. This is the positive 5 volt rail, this is the ground, and these 3 are data, latch and clock. From here, I will be connecting these terminals to the shift registers with the help of ribbon cables. So here are the incoming 5 volt, ground and other 3 signals which are connected in parallel. Because my board design is only single-sided, not always you get 100% routing. So I try my best to reach 100%. If not, then I make it as close as possible. Here you can see some of the leads which are still not connected. So I print the circuit and then later I use wires to manually connect them. This is one drawback of in-house PCB production. But the other controller board does not have this issue. It was 100% routing and worked out well. Now here is the data line that is fed into the first shift register, and the output of the last is connected to the output pin. The rest of the connections are parallel, but just because of this one line you cannot connect this board in reverse. So I marked all the boards as in and out. Elko Jacobs in his code has suggested to use SPI pins so that it's much faster to send the signals. But I'm using this really long setup and 15 shift registers, so even with SPI pins, the Arduino started having issues. Luckily, Elko Jacobs has a solution to this problem. Let me show you how. Here it is. Here he suggests that by changing the values, if this turns green, then it means that we have a functioning code. So let's turn up the crystals. Before that, I'll change the value of my shift registers to 15, and you can see here it turns into a orange yellowish color. So let's turn up the crystals value, 32 MHz. That seems to fix the problem. Well, not actually, because when I put it together on the breadboard, the Arduino did not accept the crystal. In fact, that's why I built my barebone Arduino board to test with different crystals. So let me set it back to 16. Changing the brightness did not do much, so I changed the frequency. As it is defined here, the frequency defines the speed at which the color change, and I found 50 to be the best frequency. Any less than this, then I was able to see the flickering happening. So remember to dial in these settings and make those changes in your Arduino program. In my last video, I explained the inner workings of a rotary switch. What I forgot to explain was why are there so many resistors. These are called pull down resistors and they are connected to the ground rail. When Arduino tries to read the value of the switch, it either needs to be 0 or a 1, 1 being the on state and 0 being the off state, much like 5 volt being the 1 and ground being 0. So what these resistors do is they pull down the value to the 0 and feed them into the Arduino. And when the switch is turned, because the reading is connected to the resistor instead of the ground, the positive 5 volt is fed into the Arduino, thus giving us a 1. Without these pull down resistors, all we will get is a floating value, which is of not much use. To know more how you can connect a switch to the Arduino circuit, please click on the link in the description. I would have named it as Arduino switch. Optionally, we can use a potentiometer instead of a switch, but here we will be connecting the reading pin, this one, to A0, the analog input of the Arduino. Because analog gives us value between 0 and 1024, we can divide it into 5 different sections in our code with an if-else statement and use that to light up different LEDs like this. You can download the code for the potentiometer switch from the description. Finally, why the count of 5 shift register boards? Each shift register board had 3 shift registers and then they can power 8 LEDs. So for a count of 40 LEDs, I needed 5 shift register boards. And for the power supply, yes, I could have not used the voltage regulator and used a 5 volt 2 ampere power supply. But 12 volt power supply is something I had laying around and it's very common. So I used that. Please look at the PCB etching video by clicking on the top right corner. Give this video a thumbs up if you learned something from it. If you haven't subscribed, please do subscribe to see more such videos. And follow me on Instagram to see my latest builds. Until next time, happy learning!